Hello friends, welcome to my channel. In this video I will cover quick review for production part 1. Cutting tool technology. Tool wear examples are gradual wear at back rack face and flank face, both end and side flank. And crater wear in rack face, and flank wear it happens in flank face or relief face. Flank wear can be flank wear or notch wear or nose radius wear. Mechanism for wear at tool. Different mechanisms are abrasion, adhesion, diffusion, chemical reaction and plastic deformation. Abrasion is the main mechanism for flank wear. This is very important. And diffusion is the main mechanism for crater wear. So many times asked in IAS. Then Taylor's tool equation. B t to the power n equal to constant. N is a constant or Taylor's exponent. For different tool material, n values I gave. These values are also important. For plain carbon steel, n value is 0.1. And for high speed steel, it's 0.125. Cemented carbide, it's 0.25, and for ceramic, its value is 0.6. Then effect of tool material on tool geometry. For high speed steel, positive rack angle, and its value is plus 5 degree to plus 20 degree. It's having good strength and good toughness. Then tool material cemented carbide, higher hardness and lower toughness than high speed steel HSS. And for cemented carbide, shear and tensile strength is lower than compressive strength. Back rack angle value we usually take minus 5 degree to 10 degree. For ceramic tool materials, back rack angle we usually take minus 5 degree to minus 15 degree. And it's having small relief angle 5 degree. One more thing is important here. Point angle defines strength of the cutting tool. If point angle increases, then strength of the cutting tool also increases. Effect on tool life. Parameters are V speed, F feed, D depth of cut. V is having maximum effect on tool life. Speed, then feed, then depth of cut. This is very important. V is having maximum effect, depth of cut having minimum effect on tool life. For effect on tool wear also, speed is having maximum effect and depth of cut is having minimum effect. Less effect than these two. Then work material and machinability. Aluminum is having highest machinability, its value is 5, and for brass it's 2, for copper 0.6, stainless steel 0.3, low carbon steel 0.5, cast iron 0.4. Sometimes they are asking which material among which materials is having highest machinability rating. From option they will give 4 options. Out of them you have to choose the correct one. You remember this one, aluminum and brass, they are having highest. Aluminum having 5 and brass is having 2. Then tool materials and hardness values. This is also important. First CBN is having 5000 HK. Titanium carbide TIC is having 2400 HK. L2O3 2100 HK, tungsten carbide 1800 HK, high speed steel 65 HRC. So CBN is having maximum hardness, then TIC. If in steel percentage of carbon is increases, then steel strength and hardness both increases. And for chromium, molybdenum and tungsten forms carbide in steel. If this 3% will increase in steel, then tool wear resistance also increases and machinability decreases in steel. If chromium, molybdenum and tungsten percentage increases in steel, then tool wear resistance increases and machinability decreases. Its value is decreases. In steel, machinability increases with increase in lead, sulfur and phosphorus. Or if the percentage of lead and sulfur or phosphorus increases, steel machinability also increases. This is very important. For same feed rate, larger nose radius, better surface finish, and smaller nose radius, inferior surface finish. If R increases, then surface finish also increases or surface roughness decreases. Smaller nose radius, if R decreases, then surface finish decreases, surface roughness increases. End cutting edge angle, if end cutting edge angle ECEA increases, then surface roughness also increases. Surface roughness increases and surface finish decreases. And if end cutting edge angle equal to 0, then we will get smooth surface. For turning, shaping and planing, theoretical arithmetic average surface roughness Ri equal to f square by 32R. Ri equal to theoretical arithmetic average surface roughness, f is feed, r is nose radius. So average surface roughness is directly proportional to f square, is inversely proportional to nose radius. If cutting speed or rack angle increases, then both will increase surface finish. Surface finish will increase. This graph also important, cutting speed versus log tool life. The line will linear and will like this. This graph is important. Then grinding wheel symbols. In example, they will give this type of and they will ask anyone A or 46 or H or 6 or B. It represents dash like that. From option A, B, C, D they will give. 30 represents manufacturer symbol. This is optional. A represents types of abrasive. Here A is Al2O3, and if they will give C here, then C represents silicon carbide. And 46 for grain size in mesh number. And H represents grade or bond strength. Grade is from A to Z. Here H is available. It represents bond strength. A for soft, M for medium and Z for hard. Then 6. 6 represents structure of the grinding wheel. it's from 1 to 15. Here 6. 1 for very dense structure and 15 for open structure. Then V. V represents bond type. Here V for vitrified bond. Types of bond is vitrified bond. If B is there, then resinoid bond, R for rubber bond, S for silicate bond. Then last 2 digits. This is for manufacturer's private marking. This is also optional. So many times asked in IAS. ISRO also once or twice they asked this question. Geometric feature and different processes. For very small hole less than 0.125 mm, we use this process: electron beam machining and laser beam machining, EBM and LBM. For micro machining, to cut very small parts, we are using laser beam machining and plasma arc machining and electron beam machining. For holes which are not round, EDM and ECM is suitable. And for holes which is having large depth to dia ratio, ECM and EDM is suitable. Electrochemical machining and electron discharge machining. When temperature increases, ductility also increases. If temperature increases, then yield strength decreases and strain hardening decreases. True stress K strain to the power n. K is strength coefficient, n is strain hardening exponent. K and n both depends on temperature. For Rockwell hardness test, depth of penetration is important. Here it's D, and angle of the indenter, it's cone shaped indenter or ball shaped indenter. The angle is theta equal to 120 degree. This is also important. In Vickers hardness test, indenter is pyramid shaped and theta is 136 degree, and here diagonal length is important. Then cold working. Cold working, metal forming at room temperature or slightly above the room temperature. Its advantage are greater accuracy we can achieve, better surface finish, higher strength and hardness due to strain hardening, and desirable directional properties also we can get in cold working process. Disadvantage for cold working process are higher force and power required, strain hardening reduces ductility. To overcome the strain hardening problem and reduce the force and power, we use hot working process. Here, process is performed at elevated temperature. Its temperature range is 0.5 to 0.75 of melting point temperature of the material, and strain hardening coefficient n equal to 0. For hot working process, advantages are higher ductility increases and lowers the force and power requirement, no strain hardening. Disadvantages are low dimensional accuracy and poor surface finish, strength also decreases. In cold working, strain hardening is due to slip mechanism. And hot working sequence also sometimes they are asking. This is important for IAS. If you heat the material, first stress relief will occur, then recrystallization, then grain growth. So this sequence also important. many times asked in IAS examination. Thank you friends. Thank you for watching my video. Thank you.